Well, welcome again to to our pure mathematics seminar here at UTPA. We're very happy today to have Dr. Sergey Grigorian, and he's going to tell us about flows of G2 structures.
All right. Well, thank you very much for inviting me to talk here. If I can get the microphone attached. Okay. So hopefully sound is picking up. All right, so I'm going to be talking about flows of G2 structures. So just an outline of the talk. So I'll say a few words of motivation, and then I'm going to give just an overview of G2 structures. So last semester I gave a couple of talks on the basics of G2 structures, but since there are some new faces here, I'm going to say a few more words about them as an introduction. Okay, and then we're going to look at some flows of G2 structures and some of their solutions. Okay, so basically a G2 structure is a kind of structure that can be defined on a 7-dimensional manifold. So G2 structures can be defined on a rather large class of G2 manifolds, which are rather reasonable. So they have to be orientable, and they have to admit a spin structure. So really, as far as most applications are concerned, these are pretty much all of 7-dimensional manifolds. So these special kind of structures, they are of particular interest in physics, because M theory, which is one of the interesting theories which should hopefully describe the universe. Well, it should live in 11 dimensions, right? But we only know, well, we can only see 4 dimensions, so everything else, the remaining 7 dimensions, should be some smaller space which should satisfy certain properties. And because physicists require the 7-dimensional space to be orientable, and we also need to have spinors, so the space needs to have a spin structure. So I'm not going to say in detail what that is. So just it's a spin structure, right? Then on any such 7-dimensional manifold that physicists like, we can define a G2 structure. And in particular, the exact type of the G2 structure will then depend on the precise details of the physical theory. So in this regard, it's rather important to have a good understanding of the different classes of G2 structures, and in particular how they relate to one another. And an ambitious goal would be to try and classify these G2 structures. So if you are given a 7-dimensional space, a 7-dimensional manifold, whether you'd be able to say which classes of G2 structures exist. So that's a very distant goal, which is probably not attainable in any near future, but we can always try to take some steps. Yeah. Right. So are there any where the modular space? No. So basically, we don't have any particular examples where the modular space is completely unknown. What happened? Hey, we went way too far. Okay, so one of the approaches is to actually try and study flows of G2 structures. So the idea is that we start off with some G2 structure that we know, and we try to modify it smoothly so that we eventually obtain some different kind of G2 structure. So this kind of approach has been used in geometry and topology with quite a lot of success. So in particular, the Poincare conjecture, which was a big result, proved using rich flow, which is also an example of metric flow. So this kind of approach of studying flows is generally very useful in classifying various geometric or topological structures. All right. So before we go on to the group G2 and G2 structures, let me just give a brief overview of what the group G2 actually is. And to do that, we'll need to start with octonions. So those of you who came to my talk in the fall will probably remember this. But if not, I'll give a brief overview. OK, so the group G2 is a 14-dimensional group which can be defined as the group that preserves octonion multiplication. So what are octonions? Well, so octonions, these are, well, we have the complex numbers. So we have, they split into real and imaginary part. Then we can define quaternions, which, so I'm going to write it. I'll write on the board. It's probably easier. All right. So the complex numbers. So the complex number z splits into x plus iy. Then we have the quaternions. So a quaternion can be written as some real number q plus I q1 plus j q2 plus k q3. So now there are 3 imaginary units, so to speak. All right. And the multiplication of quaternions is now non-commutative. So in particular for quaternions, a times b is in general not equal to b times a. Okay. But we can go even further. So we can now define the octonions. So now an octonion has some, so let me choose a letter, say v, has some real part v1, and then it has, well, I'm not going to write them all out, but 7 imaginary units. So we have I, j, k, and we can, well, think of other letters. But usually, since it's now too many letters, we just use numbers. So E1, E2, E3, up to E7. Right. And now octonians, they satisfy even fewer algebraic properties. So in particular, well, they are also non-commutative as the quaternions, but they are also non-associative. So for octonians, A times B times C is in general not equal to A times B times C. So we lose also the associative property. But apart from this property, we can really do many of the same things as we do with the quaternions. So back on the screen, we can define a cross product on 7-dimensional space, so on R7. So what we do is we take the pure octonions, so it's just these 7-dimensional space, and we identify them with R7. And then we can define the cross product just by taking 2 of these pure octonions, multiplying them together, and then projecting them back to the pure quaternions. So this can be interpreted as just taking 2 vectors in R7 and doing some operation to them and obtaining another new vector in R7. So the same kind of thing as the vector cross product in 3 dimensions. Well, and the group G2, it preserves this multiplication. So it fixes the real part of the octonions, and it acts on the imaginary part, so on R7, in a non-trivial way. And it also preserves the cross product. And it can also be shown that the standard inner product or the dot product on R7 is expressible in terms of octonion multiplication and is also preserved by G2. So, and in fact, G2 is actually a subgroup of SO7. So it's the group of rotations in 7 dimensions. So, in 7 dimensions, the rotations, they split into G2 and some other piece. So that's, well, that's already going more into the group theory aspects of this. So here is a diagram which can be used to work out octonion multiplication. Some of you may recognize this as the Fano plane. So if we have our 7 generators of the octonions, of the imaginary octonions, then what we do, we just follow the arrow. So E1 times E2 gives us E3, E3 times E7 gives us E4, and so on. And so we also have this circle here, so that E2 times E7 is E5. If we go in the opposite direction, we get a minus sign. And so this actually allows us just to write down the multiplication rules of the octonion. So we can encode these multiplication rules just as a set of structure constants. So to do that, we define the triple vector product. So again, this is similar to what we do in R3. So we take the cross product of 2 vectors, then we take the inner product with the third vector, and so this gives us a number overall. Okay, and so we define this operation by phi 0. So phi 0 takes 3 vectors and gives us a number. And it turns out that phi 0 is actually skew symmetric in all 3 of its indices, and so in mathematical terms, it defines a 3 form on R7. So the way we can write it down in terms of some basis for the octonions is, so here E1 to 3 just means E1, wedge E2, wedge E3. E1, 4, 5 is E1, wedge E4, wedge E5, and so on. So this just encodes the multiplication rules which we had on the previous page as a diagram. Okay. So basically, this means that E1 times E2 gives us E3, and so on. So we have 7 such pieces. Well, and G2, the group G2 preserves multiplication. So, well, preserves octonion multiplication. So it also actually preserves this object, this 3 form phi 0. So actually, we can get an alternative definition of G2, that this is precisely the subgroup of the general linear group in 7 dimensions that preserves phi 0. So we can think of this as just G2 as just 7 by 7 matrices, which are invertible, which preserve this particular 3 form. So that's the simple way of describing it. All right. So this is just an introduction of what the group G2 is. So this is just on R7. So this is the flat 7-dimensional space. What we want to do now, we want to transfer this kind of structure, the cross product, to a manifold. So a possibly curved space. Right. But before we go into that, we need a few more definitions. So so we know that this 3 form phi 0 is preserved by G2. So then we define any other 3 form, but which is in the GL7R orbit of phi 0. So it means if we take our phi 0 and we apply some general linear transformation to it, we get a positive 3 form. So this is just, we define positive 3 forms to be elements of the orbit space of phi 0. All right, so GL7 takes phi 0 to some new 3-form phi, and correspondingly the standard inner product is also taken to some new metric, some new inner product in G. So that's why these 3 forms are called positive, because to each one there is assigned a positive definite metric. Now, a simple calculation tells us that the dimension of the orbit space is 35, which is also the dimension of 3 forms in 7 dimensions. So this actually tells us that the set of positive 3 forms is an open subset of all 3 forms on R7. So in particular, this also tells us that these positive 3 forms are in some sense generic. So pretty much, well, I wouldn't say most, but generally if you pick a random 3 form on R7, it's likely to be a positive 3 form. Okay, so now let's get on to 7-dimensional manifolds. Yeah. So is the open subset dense?
To be honest, I'm not sure. Right.
What is it? Is it an analytic subset, or is it algebra? I mean, the thing that the non-positive ones is the non-positive ones. Is it an algebraic subset, or is it necessary, or is it can you write it as a solution of some certain equations? The non-positive one. So not clear.
To be honest, I mean, I would need to think about that. Right. Yeah. All right. So okay.
So now let's move on to 7-dimensional manifold. So here, what we now do is we want to define more or less the same thing, but on a curved space. So what we do is we define a smooth 3 form on the manifold such that at every point it is a positive 3 form on the tangent space. Well, so here's what happens when we do this. So at every point we have a positive 3 form. So at every point there is some copy of G2 which preserves that particular 3 form. So really what we're doing, we are selecting a particular subgroup, as a particular copy of the subgroup G2 in GL7 at every point. So what this gives us is actually what's known as a principal subbundle. So at every point we have a copy of G2 embedded in some way in the group GL7. So a precise definition of a G2 structure on the 7-dimensional manifold is that it's a principal subbundle of the frame bundle with fiber G2. So the frame bundle, it just has the group GL7 at every point, and G2 is just some subgroup of it at every point. Yeah.
Either as an atlas, or is it? Let me ask you: can you also define it in terms of saying that there's an atlas on the 7 manifold, which has chart transitions in G2?
Sure. Yes. So you can define it as an atlas. So that would be another definition. So we have the structure called G2 for the atlas. Yes. But it will give between equivalent.
That's what it appeared to me. So that's why I was asking, just to make sure I wasn't missing something.
That's true. Yes. Okay. And
important theorem is, in fact, a positive 3 form on the manifold uniquely defines a G2 structure in this sense of a bundle. And conversely, when we have this bundle, it uniquely defines a positive 3 form. So in many applications, it's much easier to work with 3 forms. So although some people may disagree, right? But if you want to do some concrete computations, usually it's easier to work with the 3 form. Okay. Okay, so let's look at some properties. Okay, so let's just recap what we have now. So let me just write on the board here. Okay, so we have a 3 form phi. So we know that at every point, this 3 form is positive. So at every point, it defines a positive metric. Right? And in fact, we can, since this is smooth, we can also get a smooth metric on the full manifold. So the metric is defined by the expression. So we take 2 vectors u and v. So these are 2 vectors. We apply the metric to it. We multiply by the volume form. So the volume form is also defined by the metric, actually. And this should be equal to 1/6. So this symbol just means that the vector is contracted with the 3 form. So alternatively, this means that we take phi, and in the first slot, we plug in a vector. And we wedge it with v contracted with phi, and we wedge it with phi again. So overall, we have a 7 form. So this thing gives a 7 form. The volume form is also a 7 form. So this is a way to actually define the metric. So it gives a non-linear definition of the metric. So because this volume form, it depends on the determinant of the metric. So it's overall quite a messy expression. But this gives us a unique metric which is associated with a given 3 form phi. Yeah. In the yeah, so this given
G2 structure, so given this positive 3 form phi, we can define a metric which is compatible. So in the sense that if we go back to the bundle picture, the G2 sub-bundle is extended to an SO7 or SO7 sometimes.
So so that metric would be the metric defining orthogonality? Is that what?
Right. Yeah.
From the
Yes.
Actually, I want to ask you a question. I think I've asked you this question like at every single talk. I can never get it from my skull. Going back to the bundle picture.
Yes.
Right. Or in the let's think about the chart picture for a second. Okay. So the chart transitions are in G2. And you're not assuming, though, that they're locally constant, though, are you?
No.
No. So that in the bundle picture, the bundles are not flat, then?
No. So that's
exactly. That's not. Okay. Yeah.
All right. So once we have the metric, we actually take
a pair phi and g in that to define the G2 structure. So in a sense, of course, we could choose any other Riemannian metric on the manifold, but we just want to specify that this is the particular metric which is compatible with this G2 structure. Okay, so we can also define the Hodge star, and hence the dual 4 form star of phi, which we denote by psi. So now, while a 3 form phi defines a metric in this unique way, actually there is a whole family of G2 structures which define the same metric. So it's not a one-to-one correspondence. So in particular, there would be the space of G2 structures or positive 3 forms which are compatible with a given metric gives an RP7 bundle. So that's SO7 over G2. Okay, so now suppose we do have this G2 structure. So we have our 3 form phi, and we have our metric G. Then existence of this G2 structure in the manifold gives us a decomposition of differential forms. So, for example, 2 forms, they split into a 7-dimensional piece and a 14-dimensional one. So this is a splitting according to representations of G2. So 2 forms, so locally can be thought of as just the Lie algebra of SO7. So the Lie algebra of SO7 splits into the Lie algebra of G2 plus the complement. So here we have the 14-dimensional piece, which is actually which comes from the adjoint representation of G2. So these are basically 2 forms such that the components are in the Lie algebra of G2. And the other piece, well, we can obtain it just by taking some vector field, any vector field, and again contracting it with phi. So that will give us a 7-dimensional piece of the 2 forms. All right, so now if we look at 3 forms, well, these split into a 1-dimensional piece, a 7-dimensional piece, and a 27-dimensional piece. So the 1-dimensional piece is actually proportional to phi, because phi is preserved by G2. So phi defines a 1-dimensional representation of G2. So lambda 3.1 can be written as just the 3 forms which are proportional to phi. Now, lambda 3.7, again, we can write these as some vector fields contracted with psi, which is star of phi. And lambda 3.27, well, this comes from another irreducible representation of G2. So these come from the traceless symmetric 2 tensors. So if you count the dimensions, this will give you 27 dimensions pointwise. And here, so this is an indices, so we contract over the index D, so that means we also have summation here over the index D, and we antisymmetrize the other 3 indices to give us a 3 form, which is Q-symmetric in all 3 indices. Okay, and similarly for 4 forms, well, this is basically just we can take the Hodge star of this decomposition of 3 forms, and we obtain a very similar decomposition for 4 forms. So again, we have lambda 4.1, which consists of 4 forms proportional to psi, which is now star of phi, and lambda 4.7 is given by 4 forms which can be written in the form some 1 form wedge the 3 form phi. Well, and lambda 4.27, well, we can just take the Hodge star of these elements of lambda 3.27. So the reason why these decompositions are important, because these are orthogonal decompositions of each of the space of each well, of the different 3 forms, and so it really is, again, simplifies calculations, because it's now possible just to split everything in the components and see what happens in each one. All right, so far what we've been looking at was really just algebra. Right? We haven't really done anything more than algebra so far. Okay, so now, okay, so again, we have this G2 structure. So we have our 3 form phi, we have our metric G. So now if we take the metric G, we can define the Levi-Civita connection nabla. Okay, so now we say that the torsion of the G2 structure is defined by nabla of phi. So we differentiate phi with respect to this Levi-Civita connection, and we see what happens. So the reason why it's not necessarily 0 is because the Levi-Civita connection is an object which is intrinsic to the metric. It's intrinsic to the Riemannian structure. So it doesn't really know about the G2 structure which we have. So it's not necessarily compatible with the G2 structure. So in fact, we can think of the Levi-Civita connection as taking values in the Lie algebra of S07, but in order for it to be G2 compatible, really we need it to be in the Lie algebra of G2. So there is an extra piece, which is the obstruction to this connection being compatible with the G2 structure. And it's expressible just by taking nabla of phi. All right. So, in fact, we can express this again in components in terms of a torsion tensor T. So the reason why this is true, and suppose we take a vector x and we take the covariant derivative of phi in the direction of this vector x. Then it's actually possible to show, it's not a difficult calculation, that this 3 form, so this is a 3 form, and that it actually lives in lambda 3.7 for any vector x. So this means, if we go back to the definition of lambda 3.7, this means that there is some vector t which depends on x, such that nabla x of phi is given by tx contracted with psi. Well, and but this is true for any vector x. So really, what we have a 2 tensor t. So we can thus write down nabla a phi b c d as some ta e psi e b c d. Right. So the x would go on this index on the left and on this index a on the right. These are just indices.
Yeah, so I'm just writing out the expression in indices, and so here we have the fraction over e. So really, we're summing.
This is the
Einstein summation.
Yeah, Einstein summation. Okay, that's what screwed me up. You don't write the sum. Okay.
No.
Yeah, you're a Riemannian geometer. I forgot.
Yes.
Like,
so if I were to write sums everywhere, then I have to do just too many sums in everything I write.
This is like crystal optical symbols.
Sorry?
Or well, Christoffel. So,
well, there was a Christoffel symbol, but
yeah,
that's applying this.
Yeah, no, but I mean the Java stuff.
Okay.
I'm thinking an analogy when you write down things in terms of symbols that you use.
Yeah. Yeah, but anyway, this is very inconvenient whenever you want to work with. Okay, so so now this torsion is actually defined completely by this torsion tensor. So this is just it can be thought of as a 7 by 7 matrix, really. So what we can do, we can also split it into pieces according to irreducible representations of things.
So in particular, we can split off the symmetric part and the skew-symmetric part. So the symmetric part then also has a trace part, which in this case is just proportional to the metric. So tau 1 is just some function, and g is the metric. Tau 27, well, that corresponds to the 27-dimensional representation, so that's just some traceless symmetric piece. And the skew-symmetric part of T, well, that's just essentially a two-form, and we know two forms split into a 7-piece and a 14-dimensional piece. So Tau 14 is a two-form with values in the 14-dimensional representation, and Tau 7, well, that's just some vector field. So this gives us a decomposition of the torsion, and this allows us to look at different torsion classes of the G2 structure. So we can think of each one of these pieces as being either 0 or non-zero, so that gives us 16 potential torsion classes. Well, also, these torsion components, they completely determine nabla of phi. So it completely determines all the derivatives of phi. So in particular, it also determines the exterior derivative of phi and d of star of phi. And we can write these down also in terms of the same components of the torsion. So d phi is a 4-form, so it has a 1-dimensional piece, a 7-dimensional piece, and a 27-dimensional one. A d of psi has a 7-dimensional piece and a 14-dimensional piece. So notice that this decomposition is orthogonal. So in order for d phi to be completely 0, all of these three components have to vanish. And similarly, if we want d psi to be 0, both of these components have to be 0. But the Tau 7 components, they're the same. So from this, we get the following corollary that, well, the first one is really just a definition that we say that the G2 structure is torsion-free if the torsion tensor vanishes completely. So this is also equivalent to saying that nabla of phi is equal to 0. And another equivalent way of saying this is that both d phi equals 0 and d psi equals 0. Because again, in order for these two to be 0, each of the 4 components of the torsion has to vanish individually. Well, if M is moreover compact, we can add an extra equivalent condition that the Laplacian of phi is 0. So the reason why torsion-free G2 structures are of importance is because this then tells us that the holonomy group of the metric G is contained in the group G2. Yeah. So the existence of a torsion-free G2 structure is equivalent to the holonomy of the metric being contained in G2. So that's so if we have a torsion-free phi with corresponding metric G, then the holonomy is in G2. So, and conversely, if the holonomy of a metric is contained in G2, then there exists a G2 structure for which the compatible metric has this holonomy group. All right. So yeah. No, it doesn't have to be flat. All right. So we can also consider intermediate cases. So we don't have to kill off all the torsion terms. We can just kill off a few. So one of the intermediate torsion classes is what's known as a closed G2 structure. So this is a G2 structure where the 3-form is closed. So d of phi is 0. And so this means that the 1-dimensional and the 7-dimensional and the 27-dimensional components of the torsion vanish, because that's what they make up d phi. So each of these components should vanish individually. Yeah.
Is torsion-free case, though.
Right. Well, this contains, right, but
So all the flat ones are contained in the torsion free.
yes, but not necessarily.
Yeah, but not in the conference, but in you. So you can contain.
Right. So these co-closed G2 structures, they sometimes go by other names. Sometimes they call calibrated G2 structures. So that goes to theory of calibrations because here phi defines calibration.
I'm not going to go into that. Oh, this keeps happening. It seems when I point this remote away from my laptop, somehow the signal doesn't quite reach. Okay, anyway, so another possibility is setting a deep side to be 0. So these are called co-closed G2 structures. So that's because the 3 form is co-closed, right? Because psi is star of phi. So if deep psi is 0, if d star of phi is 0. And so sometimes these are called co-calibrated, or even today I saw somebody call it co-symplectic. So there are different names for this again. But now, since deep psi is 0, if again we go back to the if we go back to deep psi in terms of the components of the torsion, that will tell us that the 7-dimensional component and the 14-dimensional component of the torsion have to vanish. So actually, let me go back just so that we can see this. So if deep psi is 0, then the 7 component is 0 and the 14 component is 0. Three form.
So it's not symplectic. So why would we call it co-symplectic?
I don't know. You just I saw it in the paper that some people call it co-symplectic. I don't like that. I can stand co-calibrated, and because that actually makes sense, but co-closed also makes sense, but co-symplectic doesn't make sense.
Because the complement's not a 2 form.
Yeah, I don't know.
Is it determined somehow? Is it symplectically foliated? Does that 3 form somehow determine a symplectic foliation?
Well,
like
you see,
something.
Well, what you can do if you consider, let's say, some 6-dimensional space like Calabi or something like that, process 1, then one of the components of phi would be the Taylor form, which the other part would be the circle part. So somehow you can relate it.
It's like a circle bundle over.
Yeah, I think. So if you consider your GP manifold, or rather your 7-dimensional manifold as a circle bundle of some 6-dimensional manifold, then phi has a piece which is actually the 2 form.
The 2 form for the Kähler. The 2 form for the Kähler?
Yes, yes. The which the data from the circle. All right, so yeah, but if deep psi is 0, then tau 7, tau 14 are 0, and these are precisely the symmetric components of our torsion. So
in this case, the torsion tensor is actually symmetric. Right. So we can write it down in this way, where I phi is just the map which takes symmetric tensors to 3 forms. Okay. So and also the torsion tensor T satisfies some condition that the divergence is actually equal to the gradient of its trace. So this just comes from d squared of phi equal to 0. Okay. So an interesting special case of co-closed G2 structures are the nearly parallel G2 structures. So here, suppose our torsion tensor T is proportional to the metric. So it just has the 1-dimensional component, which is defined by tau 1. Then we can it's easy to see that d phi is actually proportional to psi, and from this condition we can moreover see that tau 1 has to be constant. And moreover, what we can also say in this case is that these are, so then the metric gives us a Ricci tensor, which is a Ricci curvature, which is proportional to the metric. So these have actually positive curvature. So the Ricci curvature is 6 tau 1 squared times the metric. Okay. Why is, okay, so that's just supposed to be a Laplacian of phi. I don't know where this one came from. All right. So, okay, so let's just look at the now the Hodge Laplacian of phi. Okay, so that's just standard expression, and this is now this is still free form, so we can split it into components. So this depends on second derivatives of phi. And the first derivatives are given by the torsion, so it will depend on derivatives of the torsion. Okay. Well, and we can just try to work it out for an arbitrary torsion. Okay. So we can work out the phi 1 component. That's the one-dimensional part, so that's really just some function. We can work out the 7-dimensional part. That's some vector, and we can work out the 27-dimensional piece, which is some symmetric two-tensor, tracer symmetric two-tensor. Yeah, basically everywhere where I have repeated indices, I'm summing.
Okay, so it's formal expression. Really, you can't say much from this expression for what to be Laplace.
I never got used to that. I'm sorry.
All right, but so basically it's formal. So it's non-linear in phi, and in general it's not elliptic because so it's. I should mention
the Laplacian depends. The metric depends in a non-linear way on phi. So as an operator on phi, it becomes rather horrible. Yeah. So because all of these t's, they also depend on phi. So that's basically a horrible expression. Okay. So if we want to do something with the Laplacian, really we want to simplify things, right? So we want to look at a particular G2 structure. We can't look at a torsion-free G2 structure because then the Laplacian is 0. Okay, so we need to look at an intermediate case. So let's look at a closed G2 structure. Then our torsion tensor just has the 14-dimensional piece. So things become a lot simpler. So the one-dimensional piece is basically essentially the norm of the tau 14, the norm squared of tau 14. The 7-dimensional piece vanishes, and the 27-dimensional piece can be re-expressed such that all the derivatives of the torsion are encoded in the Ricci tensor, the Ricci curvature. So this is already something which can be worked with, so it's a much nicer expression. Okay, so this led Robert Bryant to consider the Laplacian flow of closed G2 structures. Yeah, so here Robert Bryant here
started looking into this a very, very long time ago, back in the early 90s. But then at some point he decided there was not much else that he can do, so he didn't even write down and publish what he did then. So he actually only published his results on closed G2 structures around 2003. So that was lying somewhere in his filing cabinets for 10 years. And actually, apparently now that he has more time, he is working on G2s again. So. All right. Actually, how much I started a bit late, so can I go first?
Since we're on camera, the Pure Math seminar usually starts at 3 and ends whenever it wants to. So if at 4 o'clock you have to go, you feel free to exit.
Well, I'll try not to go that much over. Okay. Okay. So let's actually let me just skip this. And I need to define what the flow is. Right. So okay, so the Laplacian flow for the G2 structure is basically just d phi by dt is the Laplacian is equal to the Laplacian. So this is this looks like a nice equation, but in fact it's actually non-linear, and so it's not quite that nice. Right. And moreover, since phi is closed, the Laplacian of phi is actually exact. It's an exact 3 form. So this flow preserves the cohomology class of phi. So once we fix the cohomology class of phi, we are evolving by an exact 3 form. So we stay within the same cohomology class. Right. So so that one of the ideas is that it should theoretically converge to a total 3 G2 structure. So so this Hitchin functional increases along the flow lines, and it has been shown
Nigel Hitchin that the critical points, the extrema of this functional, they correspond to total 3 G2 structures. So we can interpret this flow as a gradient flow for this functional.
Okay.
So this is a nonlinear equation, nonlinear operator. So what we do, we linearize it. And so it was actually done first by Zhu and Yi, and also then Bryant and Zhu. So they did it in different ways, but they got the same thing. So when we linearize it, but in the direction of a closed 3 form, so the linearization is a closed 3 form, what we get is just minus the Laplacian. So that's minus the Hodge Laplacian. So this is what we would expect. And we also have a Lie derivative term and some lower order terms. So as it happens, this is not quite parabolic. So whenever we have a flow, we want the equation to be a parabolic equation. So then everything works out nicely. We can actually prove some properties of the solutions. We can prove that there exist solutions. But this is not quite. So actually, this Lie derivative term, it causes this equation to be not strictly parabolic. So it's what's known as weakly parabolic, in that the principal symbol is not positive definite. It's semi-definite. All right. So, but here what's possible to do is applying the same kind of thing that's used for rich flow, and we just add back the Lie derivative term, and then argue that we can relate solutions of this modified flow to solutions of the original flow via some diffeomorphisms. So that's a standard way of handling this kind of thing. All right. So now let's look at the flow of co-closed G2 structure. So now what we do, we start off with something that is co-closed. So and now instead of flowing the 3 form, we're flowing the 4 form. So now d psi by dt is again the Laplacian of psi, and again this is actually an exact 4 form. This flow again preserves the cohomology class of psi. So remember, psi is closed, and we are deforming it by some exact 4 form. So we stay within the same cohomology class. And again, this flow can be interpreted as gradient flow for the Hitchin functional. So again, we would expect this, at least in some cases, to converge to G2 structures. Well, so if so the volume functional increases monotonically along this flow. So if it has extremal points, if it has maxima, then this flow should hopefully find them. So that's the idea again. Okay. Well, we can also see what happens to other quantities along this flow. So remember, we have our G2 structure. The G2 structure is being modified. So the metric, which depends on the G2 structure, also changes along the way. So and this is the corresponding flow of the metric. So again, it can be written in terms of the ridge curvature. So in fact, to leading order, this is the ridge flow. So it's the metric is being deformed by the ridge curvature and some lower order terms. So that's why it's also interesting, because it seems like these flows of G2 structures have very close relationship to ridge flow, which everyone likes because people like ridge flow. Okay.
Carolyn?
Yes, yeah, so the ridge flow was used to prove the Parabolic conjecture.
Yeah, exactly.
So the evolving form is, so the flow of the evolving form is something positive, so this shows that the volume gives increased one. Okay, however, when we do the linearization, things very similar to what we had in the previous case, but we have an extra term. And let me just say that this term actually screws up everything up. Right? Basically, it's so it's essentially this term causes our equation to be not even weakly parabolic. So it's the principal symbol becomes well, so some cases positive, sometimes negative, so it has both positive and negative eigenvalues. So basically, in this case, we can't do much. So, so let me skip this. Right. So, so in fact, in this case, we cannot apply the standard techniques. So we have to do something else. So one of the solutions is just to modify the flow in order to get rid of the offending term. So that's the easiest thing to do. So that's what I did. Okay. So what we do is we just add on an extra term, and we have some freedom just to add a constant, just for the sake of it. It may come in useful later on. So we have this Laplacian term, and also some term which depends on the trace of distortion. Okay. And actually, this term is designed in such a way to cancel out the offending term in the linearization. Okay. Okay, and then we can actually show that this new flow is weakly parabolic in the direction of closed forms, and its linearization is now what we would want it to be. However, we're not quite done yet, because we're only parabolic in the direction of closed forms. So for true parabolicity, we need to be parabolic in every direction. But here we're only parabolic in the direction of closed forms. All right. So so the idea of the proof of existence and uniqueness is that we first apply this same kind of trick used for ridge flow. So we apply the Turk's trick. So we add on that extra Lie derivative term, and so we get an equation which is strictly parabolic in the direction of closed forms. But then we also have to apply actually the original theorem which Richard Hamilton used for ridge flow, which is the Nash-Moser inverse function theorem. So that's a generalization of the standard inverse function theorem, so that now instead of working on Banach spaces, we can work on what are known as fresh spaces.
So again, this is some generalization of Banach space. And the idea is that we want to stay within space of smooth functions of smooth sections of vector bundles. So this doesn't work well with Banach spaces, but pressure spaces, they don't need a norm. So this Nash-Mose inverse function theorem gives us similar results to just standard inverse function theorem, but in the category of pressure spaces. Okay, so by applying this, we actually get short time existence and uniqueness for this flow. Okay, so let me just give an example of a simple solution. So for geometric flows, what people are interested in, which are the simplest things to do, to find soliton solutions. So a soliton is, in this setting, is basically a solution that evolves either by diffeomorphisms or scaling. So it's a self-similar solution. So it kind of stays almost the same along the flow. Okay, so for this modified coflow, one of the it's easy to see that nearly parallel G2 structures are actually soliton solutions. So actually, if we start off with a nearly G2 structure and we plug it into this flow, it will remain a nearly G2 structure, but the torsion will vary. Right. So if the torsion is proportional to the metric, it's possible to show that it will stay proportional to the metric under the flow. And then the equation for psi it can be rewritten in terms of this tau. So tau is now just a function of t. So at each point in time, it's actually constant along the manifold. So we get rather simple equations, which we can actually solve. So our psi it just changes by scale factor. So that's the whole point of a soliton solution. And so psi 0 is some initial value. The volume form is also scaled. So here we can see if this torsion is decreasing, then the manifold is stretched out. So this also remember that in this case the Ricci curvature is also proportional to the square of the torsion. So if torsion decreases, the manifold becomes bigger and bigger, so it becomes less and less curved. So that's the basic idea here. And conversely, if the torsion is increasing, the manifold is being squeezed, like it's becoming smaller and smaller, so it becomes more curved. Okay, so if we look at the case for this simple equation, we see that we have two steady-state solutions. So if tau is 0, so that just corresponds to starting with 0 torsion, and also tau a over 5. So this shows that this constant a, which we inserted, actually has a use because it gives us a new non-trivial steady-state solution. So, and if we assume that a is positive, then we see that the derivative of tau is negative if we start off between if our original tau 0 is between 0 and a over 5. Right. So in that case, torsion would decrease monotonically, and correspondingly psi would increase. So this gives what's known as an expanding solution. But if we set a equal to 0, then in every case tau would just keep increasing and psi would be decreasing. So this is a shrinking solution. And in fact, from the explicit formula for tau, we can see that we would reach a singularity in finite time. So this is what's really expected in this case. All right. Yeah, so this just shows that for some reason, leaving in this constant A actually gives us some interesting new solution. So even if it gives some interesting results in this basic soliton case, then maybe in a more complicated setting, it will also give us something interesting. Okay, so basically we're considering this flow and found it has we also lost a few things by adding this extra term. So now we cannot interpret it as the gradient flow of the Hitchin functional. So it is now not clear whether we should really expect it to converge to a torsion-free GT structure. And in fact, as we have shown from the soliton solutions, it doesn't have to, really. So, in particular, if we look at the evolution of the volume again, we see that the volume will keep increasing if the trace of T is small enough compared to A. So maybe in some situations we can control this trace of T, and in that case we would have increasing volume, which generally reduces torsion. Okay, and finally, it would still be interesting to see if we can somehow get solutions of the original Laplacian coflow from this modified flow, and because this flow looks more natural, but its analytic properties aren't as nice. So it would be nice if we could relate the two flows in some way. Right. So I'll stop here. So sorry for going over.
So do we have?
I have a question number 2. This condition. What is the meaning of first one? As the equation decide here.
Well, so the condition gives I 0 just means that we want to look at closed GT structures. Closed GT structures. So we want the size to be closed. So in particular, our initial condition would need to be a closed GT structure.
And closeness will be preserved?
Yes, closeness will be preserved.
But it's a local theory, right?
Well, no, but
existence is local or global?
Right. So you mean the existence of the solution? Right. So it's for a short time, but it's only for man.
Yeah, but it's short time.
Short time.
It will be closed. You mean on whole moment?
Yes. So it will be closed on the for manifold because the right-hand side of this equation is actually always an exact form. So
it looks like more things like continuity, not just closeness. Closeness, okay. It's closed because you can choose also epsilon small enough.
No. Well, it's here. It's maybe we're talking about the closeness because this is we're talking about the four form being closed. So D of that four form being closed.
Okay, and then your manifold is not compact, right?
Here I'm well. I am not assuming compactness here, but of course, if I want to try and interpret this as the gradient flow of the volume function, then I would have to assume compactness. So, but for existence and uniqueness,
and for stability also no compactness.
No.
One more question. More simple. In the beginning, you mentioned that each these three forms gives you G metric, right?
Yes.
And then how about geodesic and relation with this tree form along this geodesic? What can you tell about this? Along geodesic, is it invariant or not?
So yes, the tree form is very long geodesics. Okay, so well, for a general G2 structure, I would say it doesn't have to. It doesn't have to be along geodesics. So since that's a really, it's not an algebraic condition, because the relationship between the G2 structure and the metric a priori is just an algebraic condition. So
there is no geometry.
Right. So the geometry comes in once we try to specify the torsion.
But G is unique, right?
Yes, for a given 3, 4, 5, it is unique.
And no preservation of this.
Right. Yes. So for important 3-2 structure, it's would have to be because then it's because then the 3.5 is a parallel 3.10 have to be. But for a general total class. Yes.
I have a question. It's about integrability of just two structures. What are the abstractions to integrability? For example, for Riemannian structure, abstraction is a Riemann tensor, and there is no higher abstractions. But what in case of G2 structures? How many at least? What are these abstractions? As tensors.
Right. So, so do you mean abstractions?
So integrability of G2 structure. Integrability problem.
Right.
When it's locally isomorphic to flat just G2 structure. This.
Yes, I'm not sure.
At least it's a finite number of abstractions. So how many?
Right. I'm not sure.
I have a question.
Yeah.
Just do you have any information about the epsilons in the theorem? Like, I mean, if let's say the base manifold's compact, is there, can you can these local flows be extended to like somehow a global flow on the, or some kind of notion of a global flow? I'm thinking an analogy to the usual differential manifold situation. I mean, I know these are different types of flows, but I mean, or yeah, even in the soliton case, have you computed in specific examples about how how small epsilon has to be, or how big epsilon has to be, or
right. Well, in the general case, when proving this uniqueness, the epsilon just comes in, and we don't have control. We don't have any control over it. Right? So it's
right.
Well, whatever it is. Right. But of course, it's a good idea to look at some more specific cases. So in particular, something that I want to look at is a specific case where you have a 6-dimensional near-material manifold, say with a circle bundle. In that case, it may be possible to say more. So maybe in that case, it would be possible to say if you can extend this flow or something like this.
Any further questions? All right, well, let's thank our speaker one more time.